everyone. Welcome to today's live stream. I will be presenting on Penrose tilings. Now they're aperiodic rhombic tilings made using De Bruyne's multi-grid method. Okay, so let's do this screen sharing. Everything's still good. All right. All right, cool. All right, so this is the Penrose tiling. This is a non-periodic or aperiodic tiling using two rhombuses, a thick and a thin rhombus. The large rhombuses are white and the thin rhombuses are gray. Each rhombus has the same edge length on all sides, and each so there's only one edge length ever in these tilings. That is, you can make this out with toothpicks as an set of edges, and it'll come out to be is uniform edge length, basically. The tiles have angles of pi over 5 or multiples of that, such that there are 5 white rhombuses around a given node, and the thin rhombuses have half the angle, so they can fit 10 around a node. Okay. This was discovered by Sir Roger Penrose, I believe, in the 70s. Okay. So I'll go over the construction of this. It's made.
But Dugan, are you also sharing? Are you streaming your screen? I just checked the YouTube. You're showing us, but it's not.
Oh, I see. Hold on. Thank you. How do I do this? Wait, this has to go. I have to just show my screen. Okay, there we go. All right. There we go. Once again, this is the Penrose tiling. Thick and thin rhombuses. All uniform edge length. The thick rhombuses are white, and they have an angle such that 5 of them is 2 pi over 5 angle on this part of it, and the thin rhombuses are 2 pi over 10 angle here, and each rhombus is made out of four edges, all the same length. So there's only one edge length used throughout the tiling. Okay. This is made using a multi-grid method discovered by De Bruyne. So a grid is a set of parallel lines, all perpendicular to a grid vector. So I have the grid vector pointing up, and the horizontal lines are perpendicular to that, equally spaced. And I can number the grid, the space in between the grids. You can count them. So this is like the 0th one. This is the first one, the second one, and so on and so forth. So the for a point inside the certain grid spacing, you can assign a vertex, which is you take the grid vector and you go that many steps. So 0 steps, 1 step, 4 steps. Okay. If I shift the grids past the point, the stationary point, it slips into different grid spacings, and you can see the corresponding vertex moves about. Okay. So now let's look at what happens when we have two grids, red one perpendicular to this red vector and a gray one perpendicular to this gray vector. And the interstitial regions correspond to vertices. Here, if I stay within this red grid space and change the gray grid spacing, then I can advance up and down the gray vector. And if I stay within the same gray vector, gray spacing, and change my red position, then I'm changing the placement of this vertex according to the red grid vector. So each interstitial little space here corresponds to a unique vertex in the plane. Now this is a little bit more complicated. We have three vectors. Three grid vectors and three grids. And each region between grid lines corresponds to a different point on the plane.
Mm-hmm.
Okay. Once again, I can shift the each grid, and it'll change the location along that grid direction, like so.
What does grid index do? The first one?
Oh, I just changed the coloring.
Okay.
Now let's look at the shapes that correspond. Okay, so anytime two grid lines intersect, you can sample the spaces adjacent to that intersection. That is, these two gray lines intersect, and there's a space to the north, space to the east, and the south, and to the west here. So if I sample those real close to that intersection, the vertices that those correspond to form a quadrilateral, in this case, a rhombus. And the sides of the rhombuses are parallel to the grid vectors that correspond to these grid lines. So in this case, the two gray ones are here and here. So I have...
How those black points are sampled? I don't get it. Just like a random one?
Like, here, let's look at this intersection between the red one and this gray one.
Okay.
Let's shift it over there. Okay. There. Okay, so this point over here ends up there. If I sample this region, I get this point. If I sample this region, I get that vertex.
What do you mean sample? I'm still confused. It's like,
so you can sample anywhere within those open regions between the grid lines.
But it's always so it's like a fixed seed because it's always chooses the same one, right? Or what do you mean? Right? When you move it around.
Right. So if I move this point, which is mapped to here, yeah, I really should like make these different colors, I guess. But if I drag this point anywhere within this region, it's like a little hexagon. Because it never crosses one of these grid lines, the point never jumps. It only jumps when you cross over one of those grid lines.
But where it jumps is random. You just fix the random.
No, it's if I jump over this one, this point is going to move in the direction perpendicular to this one unit.
I see. Okay.
Yeah.
So it's fine.
So it's this vector is dictating which way it'll jump. So if I move it this way, it's going to jump. This is where it's kind of. So you see, it's a sum of all your grid positions relative. Okay. So if you sample the region at the four corners here, you get four vertices arranged in the shape of a parallelogram, of a rhombus. And the rhombus is going to be made from two of those vectors, the red vector and this gray vector here.
Mm-hmm.
So like, you have a copy of this here, and a copy of the red one here and here. Okay. And again, if I go to these four corners here, I get like this other rhombus of a different angle. It's because it's crossing this grid line instead of that grid line.
Yeah. And if the gray points are in the same region, it's basically gonna be degenerate some way, right? It's not gonna be a rhombus. But you can do it technically.
Like
move it to
the sample points don't have to be in a rhombic like situation, but
I mean, if you put 2 points in the same region.
Then it'll degenerate. Yeah. But insofar as if you make a rule that only two grid lines intersect at a given point, that is you avoid something like this. That is so you have three grid lines intersecting a lot of the time. Then you can't like have four corners. So the kind of thing you get there is going to be like this hexagon. If I had 6 things, it would make a hexagon. So if you stagger, if you jostle the kind of randomize the position of these grid offsets, then you can make it such that only 2 grid lines meet at a time, and you avoid having a triple point or more. In such a case, no matter what grid line intersection you look at, you'll always have a rhombus, a quadrilateral of 4 points corresponding to that intersection.
Can you set all the shifts offsets to 0? Isn't it like the point would be closer to the origin, right, of that thing? Or what? Yeah. I think it's more clear.
Mm-hmm.
Yeah, makes sense.
Walks over.
Yeah. The fun thing.
All right. So the name of the game is to set up a bunch of grid lines, go to each grid line intersection, and then plot out the corresponding rhombus according to the rule. And so the set of these grid lines is going to be dual to the rhombic tiling.
I see.
And the set of grid lines is going to be parameterized by these grid shift amounts. So the Penrose tiling is made using a pentagrid. So you set up your grids, set up these grid vectors in the shape of a equally distributed around a circle in the shape of a pentagon.
Mm-hmm.
And you go to each of these intersections and plot out these rhombuses. And depending on the breaks, sometimes you'll have a thin rhombus, or you might have a, let's see. Well, so the angle of the rhombus will be equal to the angle that the grid lines are making, just sort of at a different radial position, rotated. So
Yeah,
around this intersection, I'll get a thick rhombus. We should have. Yes. Make sure it's ordered. There we go. So this is a thick rhombus. So coding all that up. You can infer the different tile types based on the grid vectors that you choose. It'll just be pairs of them. So you have thin rhombuses and thick rhombuses, as the case may be. For this setup, up to rotation, there are only two, thick and thin. Okay. So this is the result you get when we have a triple grid. That is, the grid vectors form an equilateral triangle, and the resulting tiling of all these rhombuses is this thing. It's a uniform tiling, and it's quite periodic, and that has to do with the fact that we're using a triangular grid as the grid setup. And triangles and hexagons, they tile the plane, so there's no aperiodicity here. Now, if I change the grid so that I have angles that aren't grid vectors that are not in a triangular setup, so this is just sort of arbitrary, then the resulting rhombuses do form a non-periodic set that's sort of staggered and aliased. And shifting the grid lines around will jostle everything in discrete amounts.
That's cool.
Yeah.
Like how it's jostling.
Mm-hmm. Okay.
Okay.
So this is the pentagrid, and this is the Penrose tiling, and the offsets are all set to 0.2, and So the initial, like, one grid from each makes 10 intersections. Those intersections, hold on, let me zoom in. They have 5 intersections down here, and then 5 around there, and the corresponding tile set is these 10 around the center. And expanding out, so here I'm adding more grid lines, and these grid line intersections correspond to these tiles out here. And more grids, more tiles, increase the range, and you aggregate this tiling outward. And so this is a lot different than taking the tiles and then matching them up using matching rules and sort of doing it by hand, layer by layer. There are a lot of decisions to make when you do that, and sometimes you can get into a situation where you've made yourself into a trap and you can't like fit the gaps anymore. So this avoids that conflict. There's a Veritasium video about this some years ago.
Yeah.
Okay. You don't have to stop at 5. Wait, this is still okay. Yeah. If you alter the shifts, the tiling will jostle in certain ways, which is really interesting. That you'll flip tiles in certain lines. Sometimes more than one line at a time. And the nature of the tiling will kind of change. If you move all the grids at once, then you kind of get a pretty neat effect. You can preserve radial symmetry if you move everything symmetrically. So I should mention that all this code is available online at the Wolfram community. So if you search from go to my page here, just do a search for me and then go here. Penrose tiling using De Bruyne's multi-grid. Click to copy that code, and that's what's running this. Okay.
So is this like method? How is it different from like different? Like I don't know anything about tiling. It's just I know people also do some exact covering methods to find the tiling or something like that. Is it like a completely different method, or is it like how those techniques relate to each other? Like finding optimization and just doing grids like this.
How is it different from doing what? You're doing it by hand kind of thing?
I don't know what people do. I suppose they do some kind of optimizations, find finite like coverings. So I don't know, it's not just by hand, right? Some kind of exact cover problem, which like Boolean optimization, some sorts of this, some sorts of problem related to that. So I just wonder how those techniques, are they like completely different methods, or they
So
exactly
yeah, to compute like these tilings on a global, as far out as you want computationally, there are two methods. This is one of them. This is a two-dimensional method to construct rhombic tilings that are non-periodic, that are arbitrarily complex, and you can control the symmetry by controlling the placement of the grids and their angles. So long as you have grids that are equally rotated from each other, you can have symmetric tilings or radially symmetric tilings, but tilings that lack the translational symmetry. The other method, which I'll go into next, involves a projection from a high dimensional lattice onto a lower dimensional subspace.
Okay. So basically, this method is only for symmetric tiles, right? It's like there's no way to generate like this.
Well, you can
like hot tiles, hex. I don't know those.
Oh yeah, I don't.
Yeah, it's like there's no relationship. It's like a completely different methodology, right?
The hat tiling is different. Yeah. I haven't messed with that too much, and that seems to be like you have to aggregate it, or there's some sort of meta structure that you fill in as a substitution. So substitution tilings, that's another way to do it. You kind of have like a base figure, and then you like have a rule for taking this piece and splitting it into sub pieces, and then you split the sub pieces, so you keep like diving in and inflating the thing. Yeah, that's a different construction, possibly for a different time.
Oh no, hot tiles are already in the resource repository. Some people already can explore them very pretty easily.
That's true.
You just don't know what's under the hood.
Right.
How they work.
So here is a this is again the Penrose. Okay. This is a sevenfold tiling, rhombic tiling with sevenfold symmetry around the center. So again, take this code, copy it, paste it, run it, and have a dynamic 7 grid. And if you, this slider will like move all the grids at once in equal amounts, and you can go through a animation of tilings that all have a point at the center with rotational symmetry around that point. Kind of play with the colors too.
So there are multiple ways that are called Penrose tiles, right? They have like different, or is it the same kind of thing? It's just maybe with different shapes, but fundamentally it's the same pentagon.
I mean, this is heptagons, so there's 7 here at the middle.
Okay.
And
so there are infinite numbers, so there are some just some finite.
Oh, you can keep
set.
going. You can keep going. You can make more and more grids.
I'm just watching. I'm just looking into the Penrose style resource function, and it has some specially named shapes like obtuse triangle, acute triangle, dark kite, star, and sun for the Penrose style.
Let's see. I wonder who made it.
Lyman Hart.
Lyman.
Yeah.
Oh, okay, it's substitution then. Outline, that kind of stuff. All right. So, where's the code for this one? Yeah. I think. All right. So, as stated, you can pick a number of grids. It will make a grid vectors and equal spacing to that number of grids, and then so the Penrose is choose a gradient here. Change. Go to 7. That's the heptagonal tiling. Go to 9. Get more stuff. 11. Even more stuff. Okay, so that's fun. Then I went on to investigate like some things that happen, some interesting things that happen. All right, so if you keep the grid amounts very small, there's an interesting harmonic I like to think about it. You have a regular n-gon at the center and like a very symmetric rhombic rosette captured inside of that. And if you make it, if you make this grid variable, if you scoot the grids out away from the center too much, you kind of degrade the integrity of that. Let's manipulate. There, do you see these red ones get peeled off first, and they went over here, so they're no longer adjacent. So it used to be a like a 30 gon or whatever, and now it's kind of has it's some concave bits. And if I keep pulling outwards, then next to go will be those beige tiles, I believe. Yeah, see?
Yeah.
And then eventually there'll be like a you'll get symmetry again at value 0.5. But in any case, so if you make it small, then you have a very nice round thing in the middle. And if you set the grid range to 0, that is, you only have one grid line from every direction, then you can concentrate on those tiles that are inside the circle. Increasing the grid count and having a small uniform shift vector, you get a very symmetric rhombic rosette. Now, you can still vary the grid lines such that the total grid amounts are very small. So you're really close to the origin on the parameterization of the grid amounts. So here I have 40 grids or whatever. Yeah, 40 grids, and the grid shifts are here between like 0.0002 and 0.0010 or whatever. And each time I run this, I get like a different random thing. So there's a little wiggle room that you can play within to keep the perimeter secure and permute the tiles within. And if I set this to 0, whoops. If I set the variance to 0, then I get, whoops. There we go. I get the symmetric thing again. Okay. So, and then the question was, how can I control what happens?
Yeah.
So changing the shift amount, keeping them pinned between two different values, let's say, and confining the variation, you can confine the randomness of that rosette at will. So see what this does. Now, mind you that the set of tiles is static. So you can make a bunch of tiles, like the number of blue tiles, number of red tiles, and all that are the same. And they fill the area without any gaps each time. And there's like a million ways to permute the tiles within, while still keeping the integrity of the round thing intact.
Is there like something interesting to say about those kind of trajectories that you can draw on those when you just keep moving along opposite side of those rhombuses? Is it rhombi? Anyway.
What did you ask?
Asking you, you have this like clear paths that you can follow, right? When you start from some rhombus near the center and then just go follow from side to the opposite side, right? You can kind of make a path. So in a way you can you can somewhat foliate the whole pattern by lines, and they have different curves for different patterns.
Yeah. Oh, you're talking about this thing?
The thing, okay, show the picture, freeze it for a sec, somewhere in the middle. I'm gonna draw an example of what I'm talking about.
Okay.
Just make a picture. Any picture. No, not that. Don't complicate. Just more. What else? What else? Just stop anywhere, right? No, just make some normal pattern like you had before. This one looks crazy.
Place for this. Okay.
Yeah. Just stop. Right. For example, if you start like here, you kind of can follow the trajectory from just following the opposite side, right? Like that. So it's kind of just fix one.
Sorry, I don't know why it did that.
I'm just trying to explain what I'm talking about.
Okay,
It's like
okay.
if you pick.
Can you highlight in red then?
Yeah, it's like if you pick like any rhombus that touches the center, right? It kind of automatically gives you some path that you can follow, right? Just follow all the sides. Oh my God.
I'm sorry.
But
I promise.
like this, for example, right? If you start with this, it gets you another path. So it's kind of
yeah.
right?
Yeah, those are called ribbons. You're onto ribbons. Yeah, so you kind of follow along, going from one opposite edge to the other. Kind of like that. Yeah.
Yeah. In a way, yeah. Oh, those are basically equivalent to the sides of those, but maybe a little bit different. So is there something interesting to say about the ribbons, like for those patterns? If you just plot them, like all the, I don't know, do they have like a similar curves? Or they?
That's a very good question. I don't know what the answer is to but yeah, those are studied and there are things to say about them. you have like a network of these lines interacting, and they kind of bend about. For the Penrose tiling, those are those ribbons. I forget what they're called, but they often mirror the grid lines in a certain way. They don't deviate too much from the grid lines that in the dual.
Yeah. Interesting.
Yeah, so for instance here, you'll have these wiggly paths that kind of do that, and the next one over will let's see, like sometimes I cross, I'm not sure. Anyway, you get ribbons.
Do they cross? Hold on. I was thinking they never cross. they can cross?
They form parallel sets.
You can clear that line. It's like,
oh yeah.
It's like yeah.
Okay. I can start jostling the rhombuses at the center, and then more and more. Now, what's interesting is right, yeah. The tiling outside the perimeter is also changing, and it still exists.
Is there sorts of limit you can prescribe to this? Like, how many can you fit arbitrarily many tiles inside of this circle?
No, there's no limit. You can increase the quantity of however many grids you're looking at, and kind of pack more in.
It's kind of interesting. What would that ribbons do if you just in that limit? So like a continuous curves, especially for this one.
I think you can kind of see some of them starting here, and they straighten out, and then like it'll go like this, and like that, I think, and then kind
of. Hey guys, so sorry, I'm gonna have to leave on my side. It's a bit late here. But this is fascinating stuff. It's not the first time I see this work from Dugan, but yeah, it's always super fascinating.
I apologize online. I think I had some windows up on my left screen, and I was looking at my right screen. Wait a minute. No. Anyway, okay, Carlos.
But yeah,
thank you.
it was great. Anyway, I'll get going myself. I mean to interrupt the live stream, but yeah, great stuff, Dugan. Good to see you. See you, everyone.
See you.
Yeah, beautiful stuff.
Yeah. So let's see what else I think.
Do you have like posted some of them on demonstrations project? Something like, I don't know. I think they're very fitting for those kind of things. Just the animation, the manipulate alone.
Yeah. So that's what I was pointing at with the Wolfram community. Like this one.
Yeah, but the demonstration project is like the whole repository of this.
Oh yeah. I haven't.
That would be.
I haven't ported these to the demonstration project. I could do that.
Well, have you seen some other examples? How many other kind of tiles are there? Just to compare. If you're just gonna appreciate the beauty of tilings today, maybe we should browse some. I bet there's like many of them there. $439 demonstrations.
And tilings?
Yeah, if you search for tilings, it's a lot.
Cool.
Robinson tiling, regular tiling, compost tiling. Yeah.
Yeah, this one's fun. Some of sine curves, some of cosines. Anyway, to continue.
Names.
Yeah, everyone. All right, so here I have like a whatever it is, 10 grids, and I made this periodic somehow, some random periodic number of shifts, or maybe this is 30 grids or something. Okay, and so by manipulating the shift amounts and keeping it periodic, you can have a radius. Sure, there we go.
Oh, that's right.
So it's a radially repetitive, randomized rhombic rosette. And you can
mic drop.
Mic drop, yeah. So you take these like sinusoidal, periodic things, sample them, and you can very sufficiently, you can increase the complexity as much as you want, and it'll kind of mimic in a way the polar plot of this function, like these lobes. And then you can go back to this sinusoid and shift the theta value, or shift the phase, and kind of roll this rosette in a sort of cyclic way. And
so what you did, you basically impose this by this sine curve. You construct it yourself, then you basically made a grid that follows the same curve close to it, right? Radially. That's what you're saying.
Yeah.
What are the limitations of that? Of the curve?
The variation, the size of it has to be bounded near to 0, sufficiently close to the origin to keep the integrity of the perimeter intact. And so you kind of bound the sinusoid between small values, and the amount of shift away from the 0 will kind of dial in how much it is condensed, how much the pattern is condensed, and the number of grids will increase the number of patterns here. And since I'm using a sinusoid, I just have to phase it by 2 pi to get a animatable GIF. And this is all sort of click to copy. Here. So let's see, if I download this notebook, it should. Yeah, here's a more complicated example where I've altered it too much. So here's an example. So this is plotting the rosette and the stuff around it, and the variation is such that it dipped above the threshold where the circle in the middle is preserved, and it kind of goes back to normality.
Almost like a propeller.
Yeah.
Making waves.
Yeah, you get all kinds of like happy accidents or very interesting features that pop out of it.
So basically, you can also impose the curve instead of a circle. You can do some different sign harmonica, right?
Yeah. This just kind of undulates.
The disco ball.
Yeah. The disco
Yeah.
ball. So you can kind of see on the outside the kind of rotation that it's doing. So that's the story about rhombic aperiodic tilings and rhombic rosettes.
Cool.
A lot of fun.
Indeed.
Were there comments online? Do you see any comments?
Let's see. Just that your voice is great, so.
All right, good. Awesome. Well, all right, everyone. Go look at the code online, the Wolfram community, and thanks for tuning in.
Yeah. Thanks, everyone. See you next time. Goodbye.